We now convert our recurrence relation into a dynamic programming algorithm. We start by implementing a procedure which computes the minimum and the maximum value of the sub-expression ij through optimal values for smaller sub-expressions. So the procedure is called min and max of ij. So we first declare two variables, max and min. Initially min is equal to plus infinity, max is equal to minus infinity, or to very large number and to very small number. Then we go through all possible values of k between I and j minus 1. We just go through all possibilities of splitting our sub-expression ij into two sub-expressions from I to k and from k plus 1 to j. When such a splitting is fixed, we compute four possible values. Applying OPK to either to maximum values of this sub-expression or to minimum values, or to maximum and minimum value, or to minimum and maximum value. When such two values are computed, we just check whether one of them can improve our minimum or maximum value. If it improves, we update the min or max variable. Finally, we return the minimum value and the maximum value for our sub-expression. Our recurrent relation expresses the solution for an expression ij through solutions to smaller sub-expressions. What do we mean by saying smaller? Well, we mean just that they are shorter, right? So once again, when we compute the value for a sub-expression ij, we rely on the fact that all the values for shorter sub-expressions are already computed. This means that our algorithm needs to compute the solutions for all subproblems in order of increasing length, namely in order of increasing value of j minus I, right? So for this problem, we have roughly quadratic number of subproblems. Namely, our subproblem Ij is parameterized by the value of I and j, which in turn range from 1 to n. Right? So it makes sense in this case to store the values for all subproblems in a two-dimensional table of size n by n. Recall also that we need to solve our subproblems in the order of increasing value of j minus 1. We can do this just by going through all subproblems in an order shown on the slide. So why this order? Well, this is simply because it goes through all possible values of ij in order of increasing j minus y as required. So let's take a look. On this diagonal, we have all the cells where j minus I is equal to 0. Right? So the first cell here is 1, 1, the second cell is 2, 2, the third cell has indices 3, 3, and so on. We then proceed to this cell. Here I is equal to 1, j is equal to 2, so the difference is 1. We then proceed to this cell. This is the cell 2, 3, with the difference 1 again. We then proceed to this cell, which is 3, 4, and so on. So on this cell, on this diagonal, we have all the cells ij where I minus j is equal to 0. On this diagonal, we have all cells ij where j minus I is equal to 1. For this cell, for this diagonal, this difference is equal to 2. For this diagonal, this difference is equal to 3, and so on. So the resulting value for our initial subproblem will be computed as the value of the last cell. Right? Because this cell corresponds to the initial sub-expression from 1 to n. Now everything is ready to write down an algorithm. In the algorithm, we will maintain two tables, M and capital M. The first one for storing the minimum values for all sub-expressions, and the second one for storing the maximum values for all sub-expressions. We start by initializing these tables as follows. So when sub-expression contains just one digit, which means that when j is equal to I, then there is nothing actually to minimize or maximize because there are no operations. So there is no order on operations. So because of that, we just initialize the main diagonals of both these tables with the corresponding digits. This is done in the following loop. So m of ii and capital M of ii is equal just to di. Then we go through all possible sub-problems in order of increasing size. And this is done as follows. We gradually increase the parameter s from 1 to n minus 1. This is done in the following loop. When s is fixed, I goes from 1 to n minus s, and j is computed as I plus s. This is done to go through all possible pairs ij, such that j minus I is equal to s. Right? When I and j are fixed, we call the procedure min and max to compute the minimal and maximal value of the sub-expression ij. Right? So finally, we return the value of capital M of 1n as the result for our initial problem, because this sub-expression 1n corresponds to our initial problem, containing all digits from 1 to n. Okay, so the running time of this algorithm is cubic, namely big O of n cubed. And this can be seen by noting that we have two nested loops. So the first one with n minus 1 iterations, the first one, the inner one is with n minus s iterations, which is at most n. And also inside these two loops we have a call to min and max procedure. The running time of min and max procedure is proportional to j minus I, which is also at most n. So the running time of our algorithm is at most big O of n times n times n, which is n cubed. This slide shows an example on how tables M and capital M look like if we run our algorithm on our toy example, namely expression 5 minus 8 plus 7 times 4 minus 8 plus 9. Let's just go through this example step by step. So we start by filling in the values on the main diagonal in both matrices. So this is 5, this is 8, this is 7, this is 4, 8, 9. So this corresponds to sub-expression consisting of just one digit. So there is nothing to maximize or minimize. So we do this the same for the capital M matrix. We then proceed to the second diagonal. Well, we put minus 3 here, and this corresponds to this sub-expression. Again, in this case, there is just one operation, so there is nothing to minimize or maximize here, because, well, there is just one order when we have just one sign. So we put minus 3 here. This corresponds to the problem, to the subproblem 1, 2. Let me put all the indices here, by the way. Then we proceed to the cell 2, 3, which corresponds to this subproblem. Again, there is nothing to maximize or minimize, so we continue in the same way. In this case, it is not so interesting. And then we proceed to the third diagonal, namely to this cell. So this corresponds to the sub-expression 1, 3, which consists of 3 digits and two operations, minus and plus. So we know that one of them is the last operation in an optimal order when computing the minimum value, for example. So assume that this is minus. This will split this sub-expression into two sub-expression 5 and 8 plus 7. So for both these sub-expressions, we already know their maximum and minimum values. So once again, this sub-expression is 1, 1, corresponds to 1, 1. This sub-expression corresponds to 2, 3. So from second to third digits and from first to first digit. So we know that for the first sub-expression, we know already its minimum value, it is here, and its maximum value, it is here. So for the second sub-expression, we already know its minimum value, it is here, it is 15, and then its maximum value, it is also 15. So by going through all possible pairs of this maximum and minimum values, in this case they're all the same, we compute the minimum value, which is just 5 minus 15, it is minus 10. However, this was only the first case of splitting this sub-expression into two sub-expressions. Another possibility would be the following. So we can split it into the following two sub-expressions. So this corresponds to 1, 2, and this corresponds to 3, 3. Right? So for 1, 2 we know its minimum value, it is minus 3, and its maximum value, it is also minus 3. For 3, 3 we know its maximum value, it is here 7, its minimum value and its maximum value. Right, so then we can compute minus 3 plus 7, which gives us just 4. So for the maximum value of the sub-expression 1, 3, we select 4. For the minimum value, we select minus 10. So we proceed filling in this table in a similar fashion. So we then put 36 here in this cell, then minus 28 in this cell, and in parallel we put 60 here, 20 here, and so on. So in the end we see the value 200 here, and this is the maximum value of our initial expression. This still doesn't give us the optimal order itself, but we will be able to reconstruct it from these two tables. Now we are sure that the maximum value of our initial expression is 200, and we will find out the optimal ordering or the optimum parenthesizing in a minute.